Hi, everyone. This is Ginger Gilsdorf with Intel, and I'm joined by Tibor Szaboky from Aerospike, and welcome to this session on achieving speed at scale with Intel, Optane, persistent memory, and Aerospike. I actually did get dressed up today, but unfortunately I can't get my webcam to work, so that is a shame. Tibor and I will be going through a couple of things on persistent memory and how it works with Aerospike. The basic flow of our talk today starts with understanding the technology, a little bit about how it works, and then Tibor's got a lot of really important information, kind of the practical side of things. Once you've got your hands on persistent memory, how do you get your system ready? How do you configure Aerospike to handle it? And then what kind of optimizations can you do? And stay tuned for the end for the resources, because even if you don't have access to a system with persistent memory, there are some ways that you can try it out on your own by emulating persistent memory. Oh. Okay, I think you should be able to see the agenda now. All right, so I wanted to start by clearing up some of the confusion. There's a lot of terms that have been out in the, in the ether, in the news about this technology, and it can get a little bit confusing. The first thing you probably heard about maybe 4 or 5 years ago was 3D XPoint. That's the memory media that was designed with Intel and Micron together. And what Intel's done with that technology is taken it, added memory and storage controllers, interconnect IP, and software to work together with the media. And we refer to those 4 things together as the Intel Optane technology. So with that technology, what we can do then is make a couple different form factors. You've probably heard of the Intel Optane SSDs that are out there. There are some that are designed for the data center, and then some that are also for the client systems. And then there's also something called Intel Optane Memory, which is it's based on the memory drive technology. It allows you to kind of extend the working memory of a system. It is volatile. The form factor that we are focusing on today and that Intel and Aerospike have spent a lot of time collaborating on is called Intel Optane Persistent Memory. And this is the 3D XPoint tech media in DIMM form factor. You can see already that the capacities available are larger than what you can get in DRAM today, 128, 256, and 512 gigabyte per module. You'll also hear this referred to as PMEM or non-volatile memory. And this product, the Intel Optane Persistent Memory DIMMs, are on the market. They were launched in 2019 with the 2nd generation Xeon scalable processors. If you've seen any presentation on persistent memory from Intel, you've probably seen this tier here. What we're hoping to illustrate with this is that for a long time, you've had this gap between memory, which is small capacity but very fast, and then on the other hand, it's very costly. On the other side, you have storage, and the storage side of things have larger capacity, but they're slower. And then on the flip side, they're less expensive than DRAM or memory. So with Intel Optane Persistent Memory, this technology fits right in between the two. It has the attributes of DRAM in terms of performance and latencies, and then it has some attributes of SSD in terms of persistence and capacity. And I'll put some more concrete numbers to these terms here on a later slide. Another thing you might hear in the press are the different operating modes that Intel Optane Persistent Memory can be used in. On the left, I'm showing, in some ways, the easier mode to enable, the one that's called plug and play. It's called memory mode. And even though the persistent memory media itself is persistent, in memory mode, we're treating it as if it's volatile memory. There's an encryption key that's used As soon as the system's shut down, that encryption key is discarded, and the memory, anything that's stored on there, cannot be accessed again. But with this mode, essentially DRAM becomes the cache for your persistent memory. So your application is really only going to see, say you have a terabyte of persistent memory in your system, that's what your application sees to work with. And then anything can be pulled from persistent memory into the DRAM cache and then up through the other caches as well, up and down. So this mode is one that shows large memory. It allows you to expand your memory footprint at a lower cost, and it's completely transparent to the operating system. All of the exchange between DRAM and persistent memory is handled by the hardware. On the right side, we're seeing AppDirect mode, which is a little bit more challenging to enable for, but also gives you the benefit of the media itself, which is that it's persistent. With AppDirect mode, your applications can see whatever DRAM's in the system as regular memory, and then it also has a separate pool of persistent memory. So the application itself has to be able to distinguish and allocate memory specifically from persistent memory. With this AppDirect mode, you're getting the low latency persistent memory. Your data is persisted even across the reboot. And like I mentioned, you do have to modify your your application in order to take advantage of this. But this is what Aerospike's done. It's a little bit of extra work, but I think it has a lot of extra benefits for the end user. I'm not going to spend a whole lot of time on this, but in the links at the end of the presentation, there's some information from SNEA, which is the Storage Networking Industry Association. And this illustrates the different ways that an application can interact with a persistent memory device. I'm not going to go through all the details, but what I wanted to highlight on the right side of that diagram is the most efficient use of the technology, and it's the application being able to load and store directly to and from the persistent memory device. So it's not going through a file system or any part of the kernel. You're bypassing all of that. It's not being cached. It's called direct access, load and store from the application to the persistent memory device. And just of note, the Persistent Memory Development Kit is an industry-wide collection of software libraries that can work with any persistent memory device. And it has taken the SNEA programming model and implemented a set of libraries to help you do a lot of tasks. So there's a lot there, but you can certainly go and read more about it if you would like. Okay, with this new technology, since it is DRAM-like in speed, but we need to persist the data, we do have to do some additional work to ensure persistence. If you're working with data that's been loaded from the persistent memory device and it's in the core or the caches, once you write to that data, it's not going to be visible to your persistent memory device until it exits the caches and enters the memory controller. At that point, when it's on the memory controller, if the system were to crash, you lose power, anything that's in the memory controller will then be flushed to persistence. So you can persist these writes in two ways, one being just the normal cache pressure, but that leaves you vulnerable to, like I mentioned, system failures, and you might lose information that's in the caches. So the only way to guarantee that your writes are persisted is to add some explicit flushes. These are handled in the Persistent Memory Development Kit automatically, but you can certainly go in and do them yourself. The Aerospike index that's built with the persistent memory support chooses to flush the caches only during the shutdown process. So you need to be aware of that that if your system does crash unexpectedly, you might have lost some data and you will need to rebuild the index. The data in persistent memory version does flush during runtime, so you can be sure that any changes you make to your data are persisted. And then I just wanted to, like I said, add a few numbers to what I was talking before about persistent memory having both DRAM and SSD capabilities. On the right is showing your standard access pattern where an Aerospike client queries a data node. The data node looks it up in the index, which points directly to the data on device. So if you were to store your primary index in persistent memory, then the access latencies for DRAM, we know we're in the nanoseconds. For persistent memory, we're still in nanoseconds, but a little bit higher, maybe 2 or 3x, depending on the type of workload and the access patterns. But that's compared to SSD, which is into the milliseconds at best. In terms of capacity, for a typical 2-socket system with DRAM using 64 gigabyte DRAM DIMMs, you're going to get 1.5 terabytes of DRAM, which will store about 24 billion records, or the index for 24 billion records. With persistent memory, you can actually up that using the larger DIMMs, the 512 gig DIMMs. You can store 6 terabytes of index data, and that corresponds to 96 billion records. And then for if you were to store it in SSD, you know you've got a lot more capacity there. Persistent memory is, of course, persistent, even on a shutdown, even on a reboot. Whereas with DRAM, the only time you get this warm start is if you shut down the process, don't reboot the system, and then restart Aerospike. So there's just a little bit of the background behind Intel Optane persistent memory. And then when we go on, Tibor will be able to tell you, like I said, some of the details about how to actually implement this. So Tibor, I'll pass it off to you.
Thank you, Ginger.
Sure.
Hang on a minute. All right. I'm going to thank you, Ginger, for giving us a great overview of persistent memory. I'm going to review with you how Aerospike uses persistent memory and then how to configure it. Aerospike has 5 different configurations that provide a range of speed, cost, and scale. The data in memory and the all-flash configurations provide kind of bookends around all the various configurations. At one end, you have data in memory that provides high performance, and at the other end, you have all-flash that provides high scale or ultra-high scale. And you kind of a balanced approach with speed, scale, and cost. It kind of fits right in the middle between the 2 bookends. And what does that balanced approach give you? It gives you terabytes, petabyte scale with sub-millisecond latencies. That kind of leads us to our newest configurations, index in PMEM and data in PMEM. Index in PMEM enables Aerospike to scale 4 times at the size of index in memory and data on SSD. It also maintains a similar performance profile, and it also has the ability for fast server restarts. The restarts are measured in seconds versus minutes and hours. following in 2019, we added data in PMEM, and it's a higher performing version of our use of persistent memory. It allows us to have our reads and writes approach DRAM-like performance, yet still have the data persisted. Aerospike engineering created a rigorous design that allows for safe server restarts. They created a system of markers that guarantees the data integrity. So if there's a system outage on restart, the data that's restored is only the data that has been known to have been flushed to persistent memory. So for the rest of my talk, I'm going to take a look at how persistent memory is configured for Aerospike. First, we'll take a look at provisioning persistent memory for AppDirect mode, and then we'll take a look at how to configure Aerospike for persistent memory and AppDirect mode. After reviewing that, we'll finish up with how to optimize persistent memory with Aerospike to improve the performance of your workloads. Oops. How did I go back? There we go. First, we'll take a look at a couple of the tools that are used in managing persistent memory. The first is IPM-CTL. IPM-CTL is a utility that was developed by Intel to manage Optane persistent memory modules. It is a utility that allows you to configure or set the operational mode for persistent memory. And it allows you to set some of the other operational settings like interleaving, for example. The other tool that is used for provisioning is the non-volatile device control. It's a Linux-based utility that primarily does the segmentation of the persistent memory. It also sets the type of, or the access mode for persistent memory. Both tools have a little bit of overlapping functionality, but you can think of IPM-CTL as the tool that manages the operational behavior, whereas NDCTL is used for managing segmentation of the persistent memory. So now let's take a look at provisioning PMEM. There are 4 basic steps for provisioning persistent memory. The first is the goal, and in the process of creating a goal, you're setting the operational mode. In this case, it's AppDirect mode versus memory mode. And you also set a number of other things like interleaving. Interleaving the setting determines whether or not NVDIMMs are accessed individually or in parallel. The NVDIMMs, when they're accessed in parallel, provide a better performance. So that is the mode we prefer for running Aerospike. As a result of creating a goal, regions of persistent memory are created per socket on the system. So if you have 2 sockets in the system, you'll have 2 regions created after executing the goal creation. With those 2 regions, we can use those to create the namespaces and set the access mode for persistent memory. The access mode that we use is FSDAX, and that's File System Direct Access. And that allows you to allocate persistent memory as files and then access the persistent memory through memory mapping. As a result of creating the namespaces, you will note that a device for each namespace is created. With those devices, you can then move to the third step of the provisioning process and create a file system. There are two file systems that work with persistent memory, and that's ext4 and XFS. There are no particularly special arguments that you need to create those file systems. They both seem to work at about the same performance levels. Using the newly created file systems, we can mount those file systems correctly using the direct access option. What the direct access option, excuse me a second here. The direct access option allows the operating system to direct any traffic around the normal block I/O path and access persistent memory directly. And without that option, you'll notice that the persistent memory performance will be impacted. So it's an important setting that you shouldn't miss. Now I'm going to take a look at an example provisioning of a two-socket system. Oops. So the two-socket system, you can see that we're using 12 NVDIMMs, and the first step is creating the goal. We use IPM-CTL, and we set the app direct mode, and you notice that there is no interleaving mentioned in the command line there. Interleaving is enabled by default, so you won't see it in the command line. As a result of entering the command, IPM-CTL will respond with a list of NVDIMMs that's going to be used in the goal creation. You'll notice here that 6 of the DIMMs are on socket 0 and 6 of the DIMMs are on socket 1. You'll also notice that there's only 126 gig per NVDIMM that's listed. When you're using persistent memory, each DIMM will use a small percentage of that persistent memory as or for metadata, and so the application won't have access to that small amount of persistent memory. After you've entered it, you'll notice there's a request to confirm the operation. Once you confirm the operation, IPM-CTL will return a list of NVDIMMs that were used in the completed operation. It will also request that you reboot the system to enable the changes. Now, after you create the goal, it creates two regions, and in order to list the regions, you can use the NDCTL tool with the -R option. And you can see that there was one region created for socket 0 and one region created for socket 1. Using those two regions that were created from the goal, we can use the NDCTL tool to create the namespace. We specify the region. In this case, with the first command, we specify region 0, and then we specify the FS-DAX mode. And then as a result of executing the command, you'll see it will put out a description of the namespace that was created. What's important here is you can look at the size to make sure that the amount of PMEM is what you expected. We didn't enter any PMEM size in the command line, and so it defaults to the current available PMEM for that region. You'll notice that a block device with the label PMEM0 was created, and then when we've executed the other command, there's another block device with PMEM1. If you look in the /dev directory for your system, you should see both of those devices there. So now, using these newly created devices, we can create a file system, the ext4 file system. And here with the first command, we're creating a file system with PMEM0. The block size that was specified here was used for alignment related to the 2 megabyte pages that were used on the system. So this is the file system creation for the second namespace. And now we apply the DAX option to those two file systems that were created, and mount both file systems. So now, after mounting both file systems, we're ready to configure the persistent memory for Aerospike. Aerospike is configured through a single configuration file that's located at /etc/aerospike. The aerospike.conf file is broken down into contexts and subcontexts. The major contexts in the Aerospike config file are service, network, logging, and namespace. The namespace context defines essentially the database. It allows the different settings in terms of memory size and the type of storage you're using, whether you're using replication, that sort of thing. It is in the namespace where we do our configuration for persistent memory. So we're going to take a look at 3 different configurations of, or 3 different namespace configurations. They're going to be a progression. We're going to start with the index in memory with data on SSD, and then we're going to add to that to create the index in PMEM with data on SSD. And then we'll go ahead to the third example and show you how to modify it to create data in PMEM. So here you'll notice the namespace has the name test. The replication factor is 1. Memory is that's used is 30 gig. Sprigs is something related to the partition index. We'll go ahead and discuss that a little bit later. Now we'll focus on the storage engine. You can see here that the storage engine uses an NVMe SSD with a single partition, and it enables a write block size of 128K to write to that device. So using this as a basis, we can go ahead and make a few changes, and you'll see that you'll be able to create an index in memory namespace pretty easy. The namespace, everything at the top is the same. So you see that we kept the replication factor, the memory used, and the sprigs. The sprigs we changed to 512K for using PMEM. We also added the index type, which varies from the previous or the basic configuration, which used an index in memory. You can see in the index type, there's two configuration items. There's the mount size limit, and there's the mount point. The mount size limit says how much of the persistent memory is used for index, and the mount point is where all the 1 gig files that are used for the index are stored. And in this case, with an index of, with a mount size limit of 700 gig, you're probably going to get about 11 to 12 billion keys with this configuration. So finally, we are on our last configuration where we're configuring for data in PMEM. We have one slight modification here, and we changed the storage engine to a PMEM storage engine. And you'll notice that there's no longer a device or an SSD there. Looks like there's a question. I'll go ahead and take a look at the question toward the last few minutes here. The storage engine defines the file system direct access files that are being used to allocate the persistent memory, and the size of the files is specified in the PMEM storage engine. You'll notice that the majority of the PMEM for this region was allocated to data, and a much smaller amount was allocated to the PMEM index. So that's basically it. We've modified I've showed you how to modify a basic namespace configuration for index in PMEM and then data in PMEM. So now I want to talk about a few of the optimizations that are necessary for improving your performance with persistent memory. The first is data locality, and remote persistent memory accesses are really expensive. Your latencies will go up and your throughput will go down. So we recommend that you use on a 2-socket system 2 instances of Aerospike, 1 instance per socket, and that you pin the instance to those sockets. Now there's a few ways you can do that. You can do that with NumaCTL and manually pin it, each instance to its own socket. Or you can use Aerospike's Numa pinning mode. It's beyond the scope of the talk. It's almost a talk in itself to review the Numa pinning. You can take a look at the Aerospike website to get more details, but it is important to try and enable that for your persistent memory configurations. The next thing we take a look at are the service threads. The service threads are normally 5 times the logical cores on a server. When we're doing NUMA pinning, we set the service threads to just the number of logical cores on the system. Our third performance change was regarding the number of files that we have in the PMEM storage engine. You noticed earlier that there were 4 files. After a lot of testing and research, we determined that 4 is optimum, especially for write-only and mixed workloads. What the number of files determines is how many threads are actually hitting the PMEM or the NVDIMMs. And from some of the research, 4 simultaneous threads are kind of optimum. And looking at read-only, if you're doing a read-only workload, you may be able to increase that number a little bit. You'll have to experiment. But you would probably max out at probably 17 to 23 files. One thing to discuss when you first start a system up and load it with data is that with the FSDAX mode, you're going to trigger page faults. For every first access to a page of PMEM, it's going to trigger a page fault. That page fault is going to create a lot of latency and lower throughput. So what you want to do is try to reduce that or speed the process of the page faults up. You can do that by using 2 meg page sizes, and you can try and use a workload on your system that works through all the pages of persistent memory. Let's see, our final item to improve performance are the number of sprigs. The sprigs, the number of sprigs, after a lot of testing, we decided that 512K or better or greater is better. I think normally the number is much, much lower. It's in just a few thousand sprigs. But because of the index in PMEM, you have a higher latency when it's doing compares with the indexes that are in PMEM. You can by adding more sprigs, you flatten the tree and reduce the traversal time and improve the overall performance of the system. So as a good starting point, 512K is a good point. Finally, we have a few things before we finish up here. 2 tools that are used for monitoring persistent memory, IPM CTL and IPM Watch. IPM CTL is not just a management tool. It allows you to dump out some performance data. There's a dash performance option that is really helpful. You can also look at the IPM Watch command for performance data. It's a little more extensive. There's both an open source version and an NDA version of the IPM Watch tool. One note, if you're benchmarking or working with persistent memory, you may want to clear your data. Simply shut down Aerospike and delete all the files at your PMEM mount points, and that should clear the system, and you should be able to restart the database clean. And here's the final point of that Ginger had made earlier. If you don't have access to a system that has PMEM on it, you can emulate PMEM using DRAM. You can set a a value in your grub configuration that reserves a certain percentage of memory, and then restart your system, and it will come up as a PMEM device. Now you're thinking, well, DRAM is a much faster medium, and so it won't emulate latency. What some of the researchers have done using PMEM is to actually configure things to do remote accesses of the DRAM in order to emulate the latency that is generated through the use of PMEM.